So here we'll check out part B of number 6 from the 2010 AP exam, and it wants us to use our tangent line equation from part A. And I've already jotted that down on this screen here, tangent line's equations, y equals 8x minus 6. And we want to use that equation to approximate f of 1.1. I'm actually going to do the work here and put the approximation in place before we talk about the validity behind it. We'll do some work with this graph over here in a few minutes to hopefully convince you as to why what we're about to do is definitely valid. So we want to estimate f of 1.1. And what I'm saying here is I'm saying that the y value on f, the y value on the graph of f of x, is approximately equal to the y value on the tangent line at 1.1. And the y value on the tangent line at 1.1 is going to be found by putting 1.1 in place of the x in the equation of the tangent line. And if you evaluate this, 8 times 1.1, it's going to get you 8.8. 8.8 minus 6 is going to get you 2.8. So our estimate for f of 1.1 is 2.8. Why is that valid? Well, if we come over here to the little coordinate plane that I have set up, let's say that this is the point where x is 1, and this is the point where y is 2. So 1 comma 2 would be about right there on our graph. And I'm putting that point on the graph because, well, they told us in the problem statement that that point has to be on the graph when x is 1, y is 2, or the function value is 2. So our graph, f of x, has to go through this point. Our tangent line also goes through this point. Y equals 8x minus 6 is going to have a y-intercept of negative 6, so a y-intercept way down here, rise positive 8, run positive 1, and it's going to intersect the curve at the point of tangency at this point right here. So what I'm going to go ahead and do is I'm just going to try to draw a version of the tangent line into this graph. And I'm going to do this so it looks pretty neat here. So let me grab this real fast. And I need a line that goes through this point and through that point. So I'm saying that this blue line is the tangent line to the graph. It's the equation, it's graphed by the equation 8x minus 6. What could f of x potentially look like? Well, f of x has to go through this point. Maybe f of x looks like this, has a slope of the tangent line of positive 8 at this point, but then it travels above the line, or maybe f of x looks like this. The tangent line actually sits above f of x. We do have the slope of positive 8 at 1, but the graph sits below the tangent line. Now if you look at my graph, the way that I have this drawn, at the x value of 1.1, which would be an x value at about right here, look at my y value on the tangent line. The y value on the tangent line there is supposed to be 2.8. What's the y value on the red curve if that's what f of x looks like? Well, it's really close to 2.8. It's obviously a little bit above 2, but it's going to be a little bit beneath this estimate. Now what if the curve looks like what I drew here in green? Well, at 1.1, the y value there is going to be a little bit above the y value on the curve. Either way you draw it, if you draw the green graph to represent f of x, if you draw the red graph to represent f of x, the y value of 2.8 is going to be pretty darn close to both of these y values on the function there. Now if we look at the rest of part B, it wants us to try and decide if our approximation is greater or less than the actual value of f of 1.1. Well, if f of x looks like the green graph, f of 1.1 is above this, and so our approximation would be less than f of 1.1. But if our graph ends up looking like the red graph, the value of 2.8 would sit slightly above the function value at 1.1, and so we would have an overestimate, a value that's greater than f of 1.1. So what's the difference between the green graph and the red graph? Well, the green graph is concave up, right? Green graph's concave up. And then the red graph is concave down. So if we can determine whether or not our function, f of x, is concave up or concave down near this point of tangency, we're going to be able to figure out if our graph is above or below the tangent line and then answer the rest of part B appropriately. So let's see. the concavity of a function, that would be given by the value of the second derivative. So what's the value of the second derivative evaluated, and I'm not going to do this very specifically, I'm going to evaluate it near 1. Basically on the interval from 1 to 1.1, do we have a graph that's cupped upward? Do we have a graph that's cupped downward? So what would this be? Well, let's think about this. It tells us here that f of x, which it says y equals f of x. If f of x is greater than 0, that would mean that y is greater than 0 on the interval from 1 to 1.1. So what we have right here is we have a positive number being cubed, right? Y is going to be positive in between 1 and 1.1. What about the rest of this stuff? Well, 1 plus 3 times. So I'm evaluating the second derivative at values near 1 and ranging between 1 and 1.1 essentially. If x is between 1 and 1.1, x is positive. I'm squaring that and it's staying positive. And we just said a minute ago y is positive. So look at the value of the second derivative. I shouldn't really say approximately here. I'm not really equal to this or approximately equal to this. But near 1, the second derivative evaluated at x is near 1 is going to be a positive cubed times 1 plus something that's positive. So the second derivative is positive. This work here implies that our function is going to be concave up because of the positive second derivative, and if our function's concave up, the graph of f of x has to sit above the tangent line, and therefore our approximation for f of 1.1, this blue point, is going to be less than f of 1.1.